Great. So yeah, I'm really excited to be here to tell you about some of the work I've been doing with this awesome team at Mozilla of people whose names are on the slide, and also Dan Bonet at Stanford. And if you haven't worked with people at Mozilla, let me just first plug the experience. It's so much fun. So I'm excited to tell you about some of the work we've been doing on privacy-preserving telemetry. So the running example that I want to use throughout this talk, and this is actually what's being deployed in Nightly, is about collecting data on the effectiveness of the content blocking feature that Steve mentioned earlier today. So if you've used Firefox, you may have seen this purple shield indicating that content blocking is blocking some stuff on a web page. And what it tries to do is find these trackers like third-party cookies or these other tricky things that advertisers use to follow you around the web, and content blocking prevents those from loading. Mozilla engineers want to know things like how many times did content blocking block a tracking cookie from Facebook.com or some other origin like this. And they want this data to debug the feature and make it work better. Yeah? The way that vendors tend to collect this type of data today is by just asking their users to send this data to them directly. So you could imagine that your Firefox browser would every day send back to Mozilla a number that indicates how many times you blocked a particular tracking cookie, and then Mozilla could just sum up these numbers on their server. The problem with doing this is that Mozilla, using this kind of system, ends up becoming a single point of privacy failure in the system, right? Someone can come and steal this data. Malicious insiders potentially could abuse it, or governments could come asking for it. And this content blocking data is actually pretty sensitive because the trackers that you've seen indicate a lot about which websites you've been visiting. So you wouldn't want to give this data to Mozilla just in the clear. So this system called LibPrio that Dan and I have been working on for a number of years now essentially allows Mozilla to collect aggregate usage data about how content blocking is being used in the browser without actually having to see any individual user's sensitive data in the clear. There's a new cryptographic tool called the Proof on Secret Shared Data that makes the system possible, and I'll describe a little bit how that works. And as I mentioned, this is the basis for Mozilla's new privacy-preserving telemetry system. So this deployment is in a pilot phase, so it's enabled by default only in the Nightly browser, or the Nightly build, and I'll explain why that is. But even so, as far as I know, this is the largest deployment ever of technology based on probabilistically checkable proofs in the wild. So it's an example of a seemingly theoretical cryptographic object being used to solve a practical privacy problem. So that's one of the reasons why I'm excited about this. So let me dig into this example a little bit more to explain how the system works and how we're using it. So think of each Firefox instance, or each user I, as having a bit xi for every origin, and this bit will be set if the browser ever blocked a tracker from this origin. I'll call it site.com. And as I mentioned, these bits are sensitive because they reveal information about your browsing history. If you blocked a tracker from foxnewsnetwork.com, maybe means you're visiting a certain type of website, right? So again, these bits are very sensitive. So then for each of the, say, 2,500 known trackers on this disconnect block list, Mozilla wants the sum over all of the user's bits. So Mozilla wants to know things like how often did content blocking block a particular tracker from a particular origin, and this ends up just being a sum over these xi's. And to keep things simple, I'm just going to focus on one tracker for now, so I'll drop the superscript. Think of each browser as having a bit, and Mozilla wants the sum over all of these bits. And think of millions or hundreds of millions of bits. The way the system works at a high level is as follows. There's going to be multiple servers, could be two, could be more than two, run by different organizations. So think of Mozilla as running one server and some second organization like Stanford or ACLU or some other nonprofit running the second server. And I'll come back to this in a minute. And the way the users interact with the servers is as follows. Each user takes their private bit, and they split it into multiple pieces using a cryptographic secret sharing scheme I'll describe. They send one of each of these encoded pieces to each of the servers. And these encodings have the property that the two servers can jointly compute the aggregate statistic of interest, which is the sum of these bits, without learning anything else. The high-level security property that we get is that an attacker will have to compromise all of the servers to learn any individual user's sensitive information. So for example, Mozilla can't turn around and sell this data or can't lose this data in a data breach because they don't actually have it themselves. To be useful, the system needs to satisfy a bunch of sort of security and performance properties. So it should be correct in the sense that if everyone does the right thing, the server should get the right answer. They should get the sum of the user's bits. You can also ask for a stronger property, like the system works even if some of the servers fail and so on, but I'm not going to talk about how that works. The privacy property is the one I just mentioned. We want the system to provide security unless an attacker can compromise all of the servers. There's an extension to this. You can ask for a property called differential privacy that you can actually layer on top of the system, but again, a way I'm not going to describe. The third property is what we call disruption resistance, or DOS resistance, which is that the worst a malicious client should be able to do, so a client that's going to try to corrupt the output of the system, is to lie about the value of her input. So the worst thing a client can do if we're collecting sums of bits, a client can send a 0 or a 1, but it can't send a -5 or a 2000 or some weird value. And the last property is efficiency. So we want this thing to work at really large scale to handle, say, all of Firefox telemetry data at the rate at which Mozilla receives it from the browser. So say millions of submissions per server per hour. So there's a bunch of really nice systems for solving this type of private aggregation problem in the literature. Each of them, as far as I know, has to relax one of these 4 properties that we get, or that we want. So for example, there's systems that provide a relaxed notion of correctness, that give a very approximate answer to the aggregate statistic that you're interested in. But for this content blocking data, where we actually care about rare events potentially, the signal essentially gets lost in the noise with these systems. There are systems that use, say, relaxed privacy models, so that rely on the security of the Tor network or some type of hardware enclave. But again, these types of assumptions and sort of external dependencies are not something that we wanted for the system. And then you can also relax disruption resistance, so not provide DOS protection, or you can use heavy general purpose cryptographic tools. But in practice, again, we don't want to have to make these relaxations if we don't have to. And it turns out that with these new tools, you don't need to. So I'll describe now at a very, very high level how the system works to give you sort of a flavor of what's going on. And I think the easiest way to do this is with a strawman scheme that gets almost all the way there, but doesn't protect against malicious clients. And then I'll explain how we fix up the strawman scheme. So think of, again, there can be 2 servers or more than 2. So I've shown now with 3 servers how the system works. And each server starts out at the beginning of the day with an accumulator that's initialized to 0. And each client comes online one at a time. So each browser comes online. This browser has its secret bit as 1. And what it does is it splits its bit into 3 pieces using a standard cryptographic secret sharing scheme. So it picks 3 random numbers, modulo some big prime, that sum to the value of its bit. And it sends one of these shares to each of the 3 servers. And the idea of this type of secret sharing scheme is that if an attacker doesn't compromise all of the servers, it doesn't learn anything about the client's private bit. So the servers then add these shares into their accumulators. That client can go offline. So it's a very simple one-shot interaction from the clients to the servers. So the next client comes online. It does the same thing. It splits its data value into shares, sends 1 share to each of the servers. The servers aggregate these shares, and so on for the rest of the million clients that are going to participate in the system. So then at the end of the day, what the servers can do is they can publish the contents of their accumulators, and by summing up these 3 accumulator values, all of the randomness of the secret sharing will cancel out, and the servers will be left just with the sum of the client's bits, which is exactly what we wanted. So for example, Mozilla at the end of the day would learn that 15 phones blocked trackers from site.com, but they won't learn which phones did. So you won't leak who's visiting which website. So this strawman scheme, it feels like it got us almost all the way there. Actually, it's correct. It provides this privacy property we wanted, and it's efficient. But the reason why you can't use it in practice is that it's vulnerable to a trivial denial of service attack. And the way that works is you could imagine there's some evil ad network out there that wants to corrupt the statistics that Mozilla is computing at the end of the day. And instead of sending a share of a 0, 1 value, a bit as it's supposed to, it could send a share of a large value, like 53 or 53 million or negative 53 million. There's sort of no limit on how bad this could be. And the problem is that the privacy property of the secret sharing scheme prevents the servers from noticing that this attack is underway. So the servers will happily accept these garbage shares, and at the end of the day, they'll get a grossly overinflated value for this aggregate statistic that they want. And even worse than that, they won't know which clients caused this to happen. So this is a big problem, and this is why you couldn't use this system as described. You can fix this problem using general purpose cryptographic tools. So you can use things like multi-party computation or traditional zero knowledge proofs, but these things end up being relatively expensive. So instead what we do is we construct a new type of cryptographic tool called a proof on secret shared data that's much lighter weight and is essentially exactly the right tool for this job. So I'm not going to have time to describe in detail how this works, but I'll describe conceptually how we implement this, or essentially what the API is of this tool. So the way we use proofs on secret shared data is as follows. After the client sends its share to the servers, so I've used these brackets to indicate shared values, but before the servers actually accept these shares, what the servers ask the client to do is, in addition, send them some type of proof. And this proof essentially attests to the servers, or proves to the servers, that these shares of the x's, if you added them up, would end up with, and somehow these x's encode a 0 or a 1, that these shares are well formed or well encoded. And so what the servers can do is by checking, essentially by exchanging only a small number of bits of communication, say 200 bytes, the servers can check this proof and be convinced that if they added up their shares, they would get a 0 or a 1, and not some huge value or some other malformed value. So in essence, the servers using this proof on secret shared data idea can detect and reject malformed client submissions before they have a chance to corrupt the aggregate statistic that they're going to compute. So for example, in the Mozilla deployment, each client can influence the value of each statistic by sort of plus minus 1 at most. And after checking the proofs, then the servers do everything as before. They'll accept these values and add them into their running accumulators. So just to give you a sense of the performance improvement of this system over the prior techniques, this is a chart showing on the x-axis is the number of origins that you're reporting data about increases. It shows how the throughput of a PRIO cluster that's processing these submissions changes. So this baseline scheme with the dashed red line is showing a scheme that provides no privacy whatsoever. So this is just sending data over TLS to this cluster. And the blue line is one that provides both privacy and disruption resistance using traditional zero-knowledge proofs. And PRIO is somewhere in between. So it's something like 50x faster than the traditional approach, and it's still maybe 10x shy of no privacy whatsoever. But the point is, with this optimization, we're getting a huge savings over the prior art. So that's what I wanted to say about the tools themselves. Now I'll mention just a little bit about how this deployment in Firefox is working. So we wrote a C library called LibPrio that implements a subset of PRIO in C. And this is built on top of NSS, which is the crypto library used in Firefox. And it's only around 4,000 lines of code. So actually, this secret sharing stuff is not terribly complicated to implement. So since late last year, we've been in a sort of pilot phase of this deployment where we've implemented this code in Firefox with this team at Mozilla. And it's enabled by default only in the nightly build of the browser. And the reason it's only running in nightly is because right now Mozilla is running all of the PRIO servers. So conceivably, if the Mozilla employees got together, they could learn the private data. And so for that reason, we're only collecting essentially non-sensitive test information for the moment. And what's happening right now is a bunch of the folks on the both telemetry team and sort of security teams have been working to integrate this with the content blocking infrastructure and move the second server out to an external organization. And that's happening literally right now. The way this is getting deployed in Firefox, I'll just say at a high level, kind of looks like this. In your browser right now are the two public keys for these two PRIO servers. One secret key is held by Mozilla, and one will be held by the second server. And every 24 hours, or whenever your browser sends this telemetry ping, what will happen is, or what happens now, is your browser sends one packet encrypted to Mozilla and one packet encrypted to the second server. And a nice consequence of the secret sharing scheme we're using is that these two packets have different sizes. So the packet that you send to Mozilla grows with the amount of data that you're reporting, so with the number of origins that you're reporting data about. But the packet that you send to the second server is just an encrypted AES key, so it's a constant size thing. Which is nice because it means that the bandwidth requirements on the second server are going to be relatively modest, even if we're collecting relatively large amounts of data. So if you're a Firefox user, you can actually open up your browser and see these two public keys sitting inside your config. And if you're really enthusiastic about this, I can actually show you how to generate some proofs on secret shared data in your browser console, which at least to me is kind of entertaining. The other thing you can do is that if you're using nightly, you can open up your telemetry window. So go to About Telemetry and see this telemetry data that we're going to be collecting through PRIO, which essentially captures information about which trackers you've been blocking, or your browser has been seeing. A couple more things. So if you want to know, read a little bit more about the details of how this Mozilla integration has been going, Rob and Anthony and Eric have a blog post from late last year, and Chris has a blog post more recently about the integration with the content blocking infrastructure. So the plan is initially to collect data on something like 2,500 block list rules. So this bit will indicate which of these 2,500 rules have been triggered by content blocking in your browser. And if you look at the block list, this is this one from Disconnect that Steve mentioned. They include things like Google Analytics and AdWords and Facebook and all sorts of other stuff, including some things that to me seem kind of relatively sensitive because they, again, capture information about your browsing history. So for now, the idea is to collect data on a relatively small fraction of page loads for a relatively small fraction of clients. But the telemetry folks picked these numbers to be large enough so that they could get some sort of statistical significance for the measurements that they're going to get out. And in release, we're going to expect to process something like 200 million telemetry submissions per day. But in an initial pilot phase, I think it's going to be more like 1 million a week. And so this amounts to something like tens of gigabytes per day of data to the second server. So not huge amounts of data, fortunately. One thing I want to mention is that if you're interested in this type of work, either from a research or implementation angle, this stuff is all open source, and there's a ton of ideas that we haven't had time to implement in the browser. So things like adding support for computing not just sums over bits, but sums over larger integer types. There's a bunch of optimizations on the client and the server side that we haven't implemented, or how to add differential privacy to the system. There's also just low-level kind of C-hacking things to make the code more portable, say on Windows. And then in the next few months, we're hoping to rewrite parts of this in Rust. Actually, Fraser found a bug, a memory corruption error in LibPrio already, which kind of has been keeping me up at night, so now I think we should probably move some of this code to Rust. And then also, I think the folks at Mozilla are still looking for the right organization to serve as the second server. So if you're interested or you know someone who might be interested in doing that, please come talk to me or any of the Mozilla folks who are involved. To me, I think this is exciting because it's sort of one of the first attempts to run one of these multi-party protocols at large scale. So it would be an exciting opportunity to get in on the ground floor of this kind of thing, and I'm hoping that other companies will pick up this type of technology in the future. So just to wrap up, so LibPrio is this new system for privacy-preserving telemetry that's being used in Firefox to collect data about the browser's content blocking feature and make it better. And as I mentioned, deployment is ongoing, development is ongoing, and please come talk to me or any of the other Mozilla folks who are active in this if you're interested in helping out. And the code and the paper and the bug are here. So thanks so much.